We have learnt that the ideal gas equation describes the behavior of gases based on experimental observations. To understand the behavior of gases at the molecular level, scientists developed a theoretical model called kinetic molecular theory, KMT, or microscopic model of gases. Kinetic molecular theory is a set of 5 assumptions that describes the behavior of molecules in a gas. Let's discuss the assumptions and how they are justified in detail. Gases consist of very large number of extremely small particles called molecules, which are in constant, continuous, random, and straight line motion. During their motion, they collide with each other and against the walls of the container. The pressure exerted by the gas is due to the bombardment of its molecules on the walls of the container. The molecules of a gas are separated from each other by great distances. Hence, the actual volume of all the molecules of the gas is negligible when compared to the total volume occupied by the gas. This assumption is true as gases are highly compressible. Hence, the actual volume of all the molecules of gas is negligible. Attractive and repulsive forces between the molecules of a gas are negligible as they are much away from each other. We can state that assumption 3 is true as gases expand and occupy the entire space available to them, showing the existence of weak intermolecular forces of attraction. Hence, attractive or repulsive forces between the molecules of a gas are negligible. Individual molecules do not gain or lose energy as a result of collision. Therefore, collision between molecules is perfectly elastic. This assumption can be justified because during collision, the molecules do not settle down or slow down. The average kinetic energy of the molecules is proportional to absolute temperature. Assumption 5 is the result of the fact that when the temperature of a gas is raised, the molecules start moving faster. Thus, their individual kinetic energies increase and hence the average kinetic energy increases. Based on these assumptions, an equation for pressure of a gas is derived as PV is equal to 1 by 3 mnu square. This is called the kinetic gas equation, where n is the total number of molecules in volume V, m is the mass of the gas molecule, and u is the root mean square velocity of the molecules. Let us now understand the gas laws in terms of the kinetic molecular theory of gases. First, let's start with Boyle's law. Consider a given amount of a gas in a cylinder fitted with a frictionless piston. According to kinetic molecular theory, pressure exerted by a gas is due to molecular collisions on the walls of the container. As the number of collisions increases, the pressure of the gas also increases. The average velocity of molecules is constant at a given temperature. When the volume of a gas is decreased, the space available for the movement of molecules decreases. Then, the number of collisions on the walls of the container increases resulting in an increase in the pressure of the gas. This means, as the volume of a gas is decreased, pressure is increased for a given mass of a gas at a given temperature. This is Boyle's law. Next, let's take a look at Charles' law. Consider a given amount of a gas at normal atmospheric pressure enclosed in a cylinder fitted with a frictionless piston. When it is heated, according to kinetic molecular theory, the average kinetic energy of the molecules increases. Then, molecular velocities increase, thereby increasing the number of collisions with the walls of the container as well as the momentum of each molecule. As a result, the piston is pushed outwards. The volume of the gas then increases. Hence, at constant pressure, when the temperature of a given mass of a gas is increased, its volume increases. This is Charles' law. Next, let's move on to Avogadro's law. Consider equal volume of two gases under the same conditions of temperature and pressure. Since the temperature of the two gases is the same, according to kinetic molecular theory, the average kinetic energy of the gas molecules should also be the same. We know that the pressure of a gas depends on the number of molecules present per unit volume, as well as their average kinetic energy. As the two gases have the same pressure and same kinetic energy, they must have an equal number of molecules per unit volume. This means equal volumes of all gases under similar conditions of temperature and pressure contain an equal number of molecules. This is Avogadro's law. Gases that obey the ideal gas equation are called ideal gases. The ideal gas equation is PV equals to nRT. If we plot a graph of PV versus pressure at constant temperature, then, according to Boyle's law, we should get a straight line parallel to the x-axis, as PV is constant at constant temperature for a fixed amount of gas. However, for a real gas, we find that the plotted line is not a straight line parallel to the x-axis. This shows that real gases, which include almost all the gases such as nitrogen, oxygen, hydrogen, and carbon dioxide, show a significant or an appreciable deviation from the ideal gas behavior. When we draw a plot between PV and P for these gases, we get two types of curves. The curves for hydrogen and helium, as shown, lie above the ideal gas curve, and these two gases show a continuous increase in PV with the increase in pressure. Whereas, for other gases such as carbon monoxide and methane, the PV value first decreases with the increase in pressure and reaches to a minimum. Then, this value increases with the increase in pressure so that it crosses the straight line of the ideal gas. Thus, a negative deviation is observed initially in the curve, followed by a positive deviation as shown in the graph. Let us observe the nature of the graph obtained for a real gas in a pressure versus volume plot. It is clear from the graph that at very high pressure, the volume occupied by a real gas is more than the volume occupied by an ideal gas. And at a very low pressure, the volume occupied by both a real and an ideal gas are almost the same. Hence, at high pressure, these gases significantly deviate from the ideal gas behavior. Dutch physicist Johannes van der Waals gave an explanation for these deviations and modified the ideal gas equation in order to make it applicable to real gases. He observed that at low temperature and high pressure, the following two assumptions of the kinetic molecular theory do not hold good for the real gases. Assumption 1. There are no forces of attraction between gas molecules. Assumption 2. The actual volumes of the gas molecules are negligible when compared to the total volume of the gas. Let us see how the first assumption is modified and made applicable for a real gas by van der Waals. If the first assumption is correct, then the liquefaction of the gases wouldn't be possible. But we know that gases can be liquefied by decreasing the temperature and increasing the pressure. At high pressure, molecules of gases are very close to each other, and the intermolecular attractive forces start operating. These molecules then do not exert full impact on the walls of the container as they are dragged back by the attractive force of other gas molecules. Hence, the molecules strike the walls of the container with reduced velocity. Thus, we can say that the pressure exerted by the real gas is lower than the pressure exerted by the ideal gas. Hence, the pressure in ideal gas equation is corrected as P ideal is equal to P real plus A multiplied by N square divided by V square, where N is number of moles of the gas, V is the volume occupied by the gas, and A is the proportionality constant characteristic of a gas. In the second assumption, the actual volume of the gas molecules is negligible when compared to the total volume of the gas, which is valid only at very low pressure. But at high pressure, the molecules are restricted to move around in less volume, and hence the volume occupied by the molecules themselves becomes significant. Hence, the volume V in ideal gas equation is corrected as ideal volume minus the volume occupied by gas molecules, that is, V minus B, and for N moles of the gas, it is V minus NB. B is excluded volume, which is constant and characteristic for each gas. After substituting the two corrections of pressure and volume in the ideal gas equation, PV is equal to nRT. We get P plus AN square by V square multiplied by V minus NB is equal to nRT. This equation is known as van der Waals equation. Here, N indicates the number of moles and the constants A and B are called van der Waals constants. The values of A and B depends upon the nature and characteristics of a gas. The value of A is independent of temperature and pressure. The extent to which a real gas deviates from an ideal gas can be measured in terms of the compressibility factor Z. It is defined as the ratio of product PV and nRT. For an ideal gas, the compressibility factor Z is 1 at all temperatures and pressures because PV is equal to nRT. On plotting a graph of compressibility factor against pressure, we get a straight line parallel to x-axis at very low pressure. We find that at very low pressure, all gases have compressibility factor approximately equal to 1 and behave like an ideal gas. At high pressure, all the gases have compressibility value greater than 1. This means that these are very difficult to compress. At intermediate pressure, most of the gases have compressibility value less than 1. This means that these are easily compressible. Thus, we can conclude that real gases show ideal behavior when the volume occupied by them is so large that the volume of the molecules can be neglected in comparison to it. Hence, we conclude that the behavior of a gas becomes more ideal when the pressure is very low. The magnitude of this low pressure varies for each gas as it depends on the nature of the gas and the temperature. The graph shown here depicts the effect of temperature on the deviations shown by a nitrogen gas. The temperature at which a real gas obeys ideal gas laws over an appreciable range of pressure is known as boil temperature or boil point. The boil point depends upon the nature of the gas. The boil temperature of nitrogen is 332 Kelvin. Above boil temperature, real gases are difficult to compress and the Z value is greater than 1. Below boil temperature, real gases first show decrease in the value of Z, then reaches minimum, and with the increase of pressure, Z value increases continuously. Thus, at low pressure and high temperature, gases show ideal behavior. Let us see another significance of the compressibility factor. We know that compressibility factor for a gas is calculated as Z is equal to PV real divided by nRT. If the gas is ideal gas, then V is equal to nRT divided by P. On substituting the value of nRT divided by P in the equation for compressibility factor, we get Z is equal to V real divided by V ideal. From this, we can conclude that Z gives the ratio of the actual molar volume of a gas to the molar volume of it, if it were an ideal gas at that temperature and pressure. A gas can be converted into a liquid through a process called liquefaction. Liquefaction of a gas can occur only when the intermolecular force of attraction between the gas molecules are increased. So, how do we increase the force of attraction? It can be increased in two ways. The first method involves an increase in pressure of the gas at room temperature. When we increase the pressure, the gas molecules come closer to each other. This results in an increase in the intermolecular forces of attraction between the molecules, which leads to the liquefaction of gases. The second method involves a decrease in the temperature of the gas. As the gas gets cooled, the kinetic energy of the gas molecules decreases. This results in the decrease of the speed of their random motion and in the increase of the force of attraction between them. This ultimately results in the liquefaction of the gas. Sometimes, we need to use a combination of the both methods to liquefy a gas. For example, carbon dioxide, ammonia, sulfur dioxide, and hydrogen chloride can be liquefied either by increasing the pressure or by decreasing the temperature. There are some gases, however, which cannot be liquefied at room temperature even at very high pressure. These gases are called as permanent gases. Hydrogen, helium, and oxygen are examples of permanent gases. Irish scientist Thomas Andrews studied the pressure and temperature conditions of liquefaction of several gases. He established that for every gas there is a particular temperature beyond which, no matter how much high pressure is applied, a gas cannot be liquefied. This temperature is known as critical temperature. Critical temperature, Tc, can be defined as the characteristic temperature of a gas above which any increase in pressure will not result in the liquefaction of the gas. The minimum pressure required to liquefy 1 mole of a gas at critical temperature is called critical pressure, Pc. The volume occupied by 1 mole of a gas at its critical pressure and at critical temperature is the critical volume, Vc, of the gas. Tc, Pc, and Vc are collectively called the critical constants of the gas. A point where there is no distinction between the liquid and the vapor state of a gas is called the critical point, and the gas at this point is said to be in the critical state. In 1861, Andrews studied these critical phenomena of carbon dioxide. In his experiments, he studied the effect of pressure on volume at different temperatures for carbon dioxide. He plotted this variation in volume and pressure at constant temperature, called isotherms, as shown in the graph. Observe the isotherm at 21.5 degrees Celsius. At low pressure, carbon dioxide exists as a gas at point A. On increasing the pressure, the volume of the gas decreases along curve AB. The liquefaction of the gas starts at point B and continues along BC, which is evident by the sudden decrease in the volume. Both liquid and gaseous carbon dioxide coexist in equilibrium along the line BC. At point C, the liquefaction is complete, and the increase in the pressure has little effect on the volume. This is because liquids are very less compressible. So, a steep curve CD represents only liquid carbon dioxide. When the temperature is raised further, the horizontal portion in the graph becomes smaller and smaller, and at 30.98 degrees Celsius, it is reduced to a point represented by E. This shows that above 30.98 degrees Celsius, carbon dioxide cannot be liquefied at all, no matter how great the applied pressure is. So the critical temperature of carbon dioxide was found to be 30.98 degrees Celsius, while the critical pressure Pc is 73.9 atmospheric pressure and the critical volume is 95.6 milliliters. As you can see, all the ends of the horizontal portions of the isotherms are joined to form a dome-shaped curve as shown here. Point A represents the gaseous state, whereas point D represents the liquid state. All points within the dome-shaped area represent the existence of liquid and gaseous carbon dioxide in equilibrium. All gases on isothermal compression exhibits the same behavior as shown by carbon dioxide. Note that it is possible to change a gas into a liquid or a liquid into a gas, such that there is always a single state present by altering the conditions of temperature and pressure. For example, in the graph, as we can move from point A to point F vertically by increasing the temperature, point G can be reached by compressing the gas at constant temperature along the 31.1 degrees Celsius isotherm. As the curve FG lies above the critical temperature, increase in the pressure doesn't result in the liquefaction of the gas. Hence, curve FG represents the gaseous state. Now, if we move vertically down from point G by lowering the temperature, on crossing the critical isotherm at point H, we get the liquid state. Thus, at no stage during the process we crossed the two-phase region. This is called the continuity of state. To recognize this continuity, the term fluid is used for either a liquid or a gas. Thus, a liquid can be viewed as a very dense gas. A gas can be liquefied below critical temperature by applying pressure, and then it is called the vapor of the substance. For example, carbon dioxide gas below its critical temperature at 30.98 degrees Celsius is called carbon dioxide vapor. Let us start with vapor pressure. When a liquid is partially filled in a closed evacuated container, the molecules of the liquid that possess above average kinetic energies overcome the intermolecular forces that hold them in the liquid and rise to the surface. These molecules start escaping from the surface of the liquid and reach into the vapor state. The process by which molecules of a liquid go into the vapor state from the surface of the liquid at any temperature below the boiling point of the liquid is called evaporation. As the molecules escape into the vapor state, they get confined to a limited space above the liquid and start moving randomly. During their motion, they collide with each other, with the walls of the container and with the surface of the liquid itself. When these molecules collide with the surface of the liquid, they are attracted back to the liquid. This process is called condensation. During the initial stages of evaporation, the rate of evaporation is higher as compared to the rate of condensation. After some time, as the rate of condensation increases, the number of molecules present in the vapor state starts decreasing. Gradually, a stage is reached when the rate of evaporation becomes equal to the rate of condensation. At this stage, there is no change in the level of the liquid in the vessel, and the system is said to be in dynamic equilibrium, where rate of condensation is equal to rate of evaporation. At this stage, the vapor pressure of the liquid is referred as equilibrium vapor pressure or saturated vapor pressure. Thus, vapor pressure may be defined as the pressure exerted by the vapor present above the liquid in equilibrium with its liquid at a given temperature. Since the formation of vapor depends on the temperature of the liquid, vapor pressure is also a function of temperature. Let us look at what happens when a liquid is heated in an open vessel. Initially, the liquid vaporizes only from the surface. On further increase in the temperature, vaporization occurs freely throughout the bulk of the liquid and vapor pressure rises. After some time, a stage is reached when the vapor pressure of the liquid becomes equal to the external pressure. This stage is called boiling, and the temperature at which boiling takes place is called the boiling point of that liquid. Hence, boiling point may be defined as the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure. Do you know why food cooks faster in a pressure cooker? The boiling point of a liquid varies with the pressure. An increase in the pressure over the surface of the liquid increases the boiling point. In the pressure cooker, by covering the vent with a weight, the pressure inside the vessel is increased above the atmospheric pressure. Due to this, the boiling point of water also increases, and hence the food cooks faster. At high altitudes, the atmospheric pressure is low, and hence the water boils at low temperatures at these places. Hence, people living at higher altitudes use pressure cookers to cook food. The sterilization of the surgical instruments in autoclaves also utilizes the same principle as used in the pressure cookers. If the external pressure is 1 atmosphere, the boiling temperature is called the normal boiling point, and if the external pressure is 1 bar, the boiling temperature is called the standard boiling point of the liquid. The standard boiling point of a liquid is slightly lower than the normal boiling point, as 1 bar pressure is slightly less than 1 atmosphere pressure. For example, the standard boiling point of water is 99.6 degrees Celsius or 372.6 Kelvin. And normal boiling point of water is 100 degrees Celsius or 373 Kelvin. The variations in the vapor pressure of various liquids with temperature are as shown here. From the graph, you can see that the vapor pressure of a liquid increases with an increase in its temperature. That is, at normal room temperature, 298 Kelvin or 25 degrees Celsius, liquids like carbon tetrachloride, ethyl alcohol and water have a low vapor pressure. These liquids with low vapor pressure have a high boiling point and do not readily evaporate at room temperature. At room temperature, as diethyl ether has high vapor pressure, it has a very low boiling point. Therefore, it evaporates readily at room temperature. Let's now discuss about surface tension. This property of liquids arises from the intermolecular forces of attraction. A molecule in the interior of a liquid experiences equal intermolecular forces of attraction from all sides. Therefore, a single molecule in the bulk of liquid does not experience any net force. However, the molecules on the surface experience a net downward attractive force towards the interior of the liquid due to the molecules below it. Thus, we see that there is a tendency on the part of the surface molecules to go into the bulk of the liquid. The liquid surface is therefore under tension and tends to contract to the smallest possible area in order to have the minimum number of molecules at the surface. The attractive forces have to be overcome in bringing the molecules from the bulk to increase the surface of the liquid. This requires expenditure of energy. The energy required to increase the surface area of the liquid by 1 unit is defined as the surface energy. The units of surface energy are joule per meter square. Surface tension may be defined as the force acting at per unit length perpendicular to the line drawn on the surface of liquid. It is denoted by gamma and is measured in kilogram per second squared. Its SI unit is Newton per meter. To avoid the instability caused by the surface tension and to remain at the lowest energy state, liquids naturally tend to have the minimum number of high energy molecules on the surface. To minimize the surface area as much as possible, the molecules of liquids assume the shape of a sphere. This is why mercury forms spherical beads instead of spreading on a surface. For the same reason, sharp glass edges are heated to smooth them. On heating, the glass melts and the surface of the liquid tends to assume rounded shape at the edges. This makes the edges smooth. This is called the fire polishing of glass. Due to surface tension, a liquid rises or falls in the capillary tube as soon as the capillary touches the surface of the liquid. Liquids wet the things because they spread across their surfaces as thin films. The particles of soil at the bottom of a river remain separated but are pulled together when taken out. This is because of the reduction in the surface area of the thin film of water. The magnitude of the surface tension of a liquid is directly proportional to the attractive forces between the molecules. This implies that the larger the attractive force, the higher the surface tension of a liquid. surface tension decreases with an increase in temperature. This is because at higher temperature the kinetic energy of the molecules increases. This reduces the intermolecular attraction, resulting in a decrease in the surface tension. Let us now look at another important characteristic property of liquids: viscosity. We can observe that certain liquids flow faster than some other liquids. For example, water flows faster than honey. This is due to viscosity. Viscosity is a measure of resistance to flow in liquids, which arises due to the internal friction between the layers of the fluid as they slip past one another when the liquid flows. When a liquid flows over a fixed surface, the layer of molecules in immediate contact with the surface is stationary, while the upper layers move with different velocities. The velocity increases with the distance of the layers from the fixed layer. This implies that the uppermost layer of molecules has the greatest velocity. This type of flow, in which there is a clear gradation of velocity from one layer to another, is called laminar flow. As shown, for any layer in a laminar flow, the layer above it accelerates its flow, whereas the layer below it retards its flow. The velocity gradient is calculated as the difference in velocity between any two layers of the fluid, represented by du, divided by the distance between them, represented by dz. A force maintains the flow of layers, which is directly proportional to the area of contact of the layers and the velocity gradient. This implies that the force required for maintaining the flow of layers is a function of the velocity gradient and the area of the layers. In the equation shown, eta is the proportionality constant and is called the coefficient of viscosity. The coefficient of viscosity is defined as the tangential force per unit area required to maintain the unit difference of velocity between two layers unit distance apart. The SI unit for the viscosity coefficient is 1 Newton-second per square meter, which is identical to 1 Pascal-second. In the CGS system, the unit for the coefficient of viscosity is poise, named after the great scientist Jean-Louis Poiseuille. An increase in viscosity decreases the flow of a liquid. An example of a highly viscous liquid is the glass. Glass is so viscous that it would take years to move a few inches. The mobility of glass can be noticed by measuring the increased thickness of the window panes of old buildings at bottom of the window pane. An increase in temperature decreases the viscosity of liquids. At high temperatures, the molecules have high kinetic energy to overcome the intermolecular forces, thus allowing the liquid layers to pass over each other.